Hi everyone, in this lecture we will show how to build a linear model that maximizes the Sharpe ratio. The key insight is that the parameters of this model can actually be computed analytically. That means you don't need to set up and solve an optimization problem to find the best parameters. Instead, you can calculate them directly using just a few simple mathematical operations on your data. This approach gives you two major advantages. First, the analytical solution is much faster, often several orders of magnitude faster than running a full numerical optimization. Second, unlike numerical optimization, the analytical solution guarantees that you get the truly optimal, best possible result. At the end of the lecture, we will also show that linear models are more powerful than they might seem at first glance. In fact, we will demonstrate how they can be used to construct complex nonlinear models capturing complex patterns in the data. To illustrate our approach, we will be working with real market data. Specifically, we will load Apple's stock prices using the Yahoo Finance library. This library is completely free to use and no registration is required. In cell 1, we import the library. In cell 2, we load Apple's stock data by specifying its ticker symbol and the time range we're interested in. In cell 3, we check the size of the dataset and see that it contains over 11,000 trading days. In cell 4 and 5, we print the first two and the last two rows of the table. The quick check shows us that the dataset has 6 columns: date, open, high, low, close, and volume. The first step we do is some basic data formatting. In cell 9, we rename the columns to shorter names, which makes the code cleaner and easier to read later on. In cell 11, we reorder the columns, for example, placing open first and close last, so that they appear in a more intuitive order. Finally, in cell 13, we display the result of these formatting changes. Now, to apply machine learning, we need to define features and a target. So let's add them to our dataset. In cell 9, we create a new column for the relative price change, which will serve as our target. Notice that we define it using tomorrow's close compared to today's close. This makes it a future price change, not a past or a present one. There are other ways you could define the target depending on what you want to model. If you are interested in the intraday changes, you would compare tomorrow's close to tomorrow's open. If you are interested in overnight moves, you would compare tomorrow's open to today's close. But for our purpose, we will use the close to close change, since that's the most common case. In cell 10, we introduce a few features. Let's go line by line. First, we compute minimum and maximum value of the close price over the last 15 days. Then we check where is the last close in the range defined by the minimum and maximum. That way we get our first feature named range. After that, we calculate the current daily price change for each date. This value will serve as the basis for several additional features. First, we compute the average daily price change over the last 15 days and over the last 30 days. Both of these averages become our features. Next, we take the ratio of the two averages, the 15-day mean divided by the 30-day mean. This ratio, which we will call red, will also be used as a feature. Next, we compute the variance of daily price changes over the last 15 days. Finally, we calculate two higher order statistics, skewness and kurtosis, this time over the last 30 days. With this, we conclude our initial set of feature calculations. In cell 11, we filter the dataset to prepare it for machine learning. First, we keep only the 7 feature columns along with the target. Second, we remove any rows that contain missing values. In cell 12, we print the result. This final clean dataset is what we will use for our machine learning experiments. Before jumping into machine learning, let's establish a baseline, what we get without using any modeling. Since our goal is to maximize the Sharpe ratio, we start by defining a helper function in cell 19 called getSharpe. This function calculates the Sharpe ratio as the mean return divided by the standard deviation, with an additional scaling factor of square root from 252 to annualize the result. Why square root of 252? Because there are about 252 trading days in a year. So this factor converts our daily Sharpe ratio into an annualized one, making it easier to compare with standard benchmarks. In the next cell, we plot the cumulative sum of daily returns. This corresponds to a very simple strategy: holding the same number of shares every day without making any adjustments based on the values of our features. As we can see, the result isn't very impressive. The Sharpe ratio of this strategy is only about 0.15, which is quite low. Now let's try a random linear strategy. In cell 60, we start by generating 8 random parameters. Using these parameters, we define our position, that is how many shares we want to hold on each day. First, the position is set equal to the first random parameter. This acts like a baseline. Then we adjust the position by adding each feature multiplied by its own feature-specific parameter. In other words, our position is simply a linear function of the 7 features. Next, we calculate the daily profit, often called the daily return. It's defined as the product of the price change and our position. This is quite intuitive. The gain or loss from a price movement is proportional to our position, which is the number of shares we are holding at that time. Let's see what this random linear strategy gives us. In the next cell, we plot the cumulative sum of daily profits along with the corresponding Sharpe ratio. This time the Sharpe ratio is about 0.32, roughly twice as good as the constant feature-independent strategy we started with. But keep in mind, this improvement came purely from a random linear function, we just got lucky. Now comes the real question: what Sharpe ratio can we achieve if, instead of relying on chance, we deliberately search for the best possible linear function? Before introducing our analytical method, which gives the optimal parameters of the linear function that maximizes the Sharpe ratio, we will first try a more straightforward approach, direct numerical optimization. To set this up, we need a few auxiliary functions. In cell 17, we define a function called addProfit. It takes 2 inputs. The first one is our dataset containing the features and the target. The second one is a list of 8 parameters for the linear function. Using these parameters, the function calculates the positions and the corresponding profits, and then adds them as 2 new columns to the table. Next, in cell 18, we define a cost function. This function is necessary so that we can apply the numerical optimization tool provided by the SciPy library. The function takes a list of model parameters as input. It then computes the Sharpe ratio of the corresponding strategy and returns its negative value. Why negative? Because SciPy's optimizers are designed to minimize a function. Since our goal is to maximize the Sharpe ratio, minimizing the negative Sharpe ratio achieves the same effect. In cell 19, we test a simple case, setting the position to 1 and multiplying all the features by 0. In other words, completely ignoring the features. As expected, this gives us a Sharpe ratio of about 0.15, which is exactly the baseline result we saw earlier. In cell 20, we run the optimization to search for the parameters that maximize the Sharpe ratio. Then in cell 21, we examine the results. First, we normalize the parameters. Here's why. Scaling all parameters up or down scales the positions by the same factor. That, in turn, scales both the mean and the standard deviation of returns proportionally. Since the Sharpe ratio is defined as the ratio of mean to standard deviation, the scaling cancels out and the Sharpe ratio remains unchanged. This means we are free to rescale the parameters so that their absolute values never exceed 1, which is exactly what we do in cell 21. As output, we see the optimized parameters along with the corresponding Sharpe ratio about 0.75. But numbers only tell part of the story. Let's take a look at the visual results. Here we have the figure showing the found strategy, the blue line. For comparison, we also plot the original constant position strategy, where the position does not depend on any features. As in the previous lecture, to compare two strategies fairly, we need to normalize them. There are 2 common ways to do this. Either scale them so that their average daily profit is the same, or scale them so that their volatility or standard deviation of daily profit is the same. In this case, we normalize by volatility. We scale the strategies so that their daily profit standard deviation are the same. And what do we see? For the same level of risk, the optimized strategy earns significantly higher returns than the baseline. Now let us look at the promised exact analytical solution. We have implemented it as a small class with fit and predict methods matching the familiar scikit-learn interface, the standard machine learning library in Python. As you can see, the solution is really small and simple. Let us walk through it line by line. In the fit method, we start with a 2D array of features and a 1D array of targets. First, we prepend a column of ones to the feature matrix. Next, we multiply element-wise each column of this extended feature matrix by the targets column. Then we calculate covariance between all the columns of this 2D array. Finally, we take the inverse of the covariance matrix and multiply it, on the right, by the vector of column means. And that's it. This gives us the parameter of the optimal linear model that maximizes the Sharpe ratio. You might be wondering why this method works. Although the full derivation goes beyond the scope of this lecture, and you don't really need to know it to be able to use the method, I will give you a rough intuition to satisfy your curiosity. Suppose we have 8 features. From each feature we can construct a simple strategy where the feature itself as it is used as a position. That gives us 8 strategies plus the original instrument, so in total we effectively have a portfolio of 9 instruments. Our goal then becomes, how do we build the optimal portfolio of these instruments in the sense of maximizing the Sharpe ratio? This is a classic problem with a known solution. Compute the covariance matrix of the instruments, invert this covariance matrix, multiply the result by the vector of mean returns, and that's exactly what we did in our analytic solution. Now let us see how this model is actually used and what results it gives. In cell 48 we create an instance of our model, which we call ls. We then extract the x and y, features and target arrays, from the pandas data frame. Next we feed the model to the data. After that we use the trained model to generate positions that maximize the Sharpe ratio. If you have worked with scikit-learn, you will notice that this workflow feels very familiar. We just feed the model and then predict the outputs. However, here the predictions are optimal trading positions instead of predictions of targets. Once we have the positions, we immediately multiply them by the price change to compute the corresponding profits. In cell 49 we calculate the Sharpe ratio for our analytical solution. It turns out to be about 0.79, which is slightly better than the result we obtained from numerical optimization. This highlights 2 important points. The analytical solution is much faster, since it avoids the iterative search process. And most importantly, it always gives the exact optimal result. Next, in cell 50 we print the parameters of the analytical model. Then in cell 51 we print the parameters from the numerical optimization so that we can compare the two. As you can see, the results are broadly similar, but with noticeable differences showing that the numerical optimizer didn't quite reach the true optimum. Finally, just to double check our results, we run the strategy again using the add_profit function. This time we only need to give the parameters of the model as the second argument. As expected, we get the same result. At first glance you might dismiss linear models as being too simplistic. After all, they assume only a linear dependency, which is not flexible enough to capture the complex nonlinear patterns we might encounter in real data. To illustrate this, let's start with the simplest case, a model with just one feature. In that case, a linear model reduces to the first formula, which contains only 2 parameters, C0 and C1. And you would be absolutely right to think this looks like a very limited function, hardly capable of describing complex patterns or dependencies. What you might really want is something like a polynomial function given by the second formula. It includes many nonlinear terms and many more parameters. By adding higher order terms, you can make the function as flexible and expressive as you want, able to approximate arbitrary complex patterns. Now here is the surprising part. Even a complex polynomial model still falls under the umbrella of linear models. Why? Because when we estimate the parameters of a polynomial model, we can apply the same analytical solution we derived earlier for linear models. Let's see how this works in practice. First we create a new data frame. We keep only one original feature, range 15, along with the target. We then rename this feature to f1. Next we generate additional features by taking different powers of f1, squares, cubes and so on. We name them f2, f3 and so on. By now you are probably starting to see how this works. On one hand, we are just fitting a linear model over many features, but in this case all those features are simply different powers of the same original feature. So while the model is linear in terms of its parameters, the resulting function introduces a complex, non-linear dependency on that single feature. This image shows how we capture increasingly complex dependencies as we rise the order of the polynomial. We begin with a simple linear dependency shown by the blue line. Just as a side remark, this already looks like a trend-following strategy. We use range 15 as the feature, and the model suggests that when the current close is near the 15-day maximum, the market is likely trending up, so we should buy. Conversely, when the close is near the 15-day minimum, the model spots a downtrend, so selling would be profitable. Next, we move to a more complex quadratic dependency shown in orange. This still behaves like a trend-following strategy overall, but it introduces a subtle correction. If we take the model literally, it suggests a possible trend reversal effect. When the close is very close to the 15-day minimum, the model expects a reversal and advises buying instead. As we continue to increase the polynomial order, we can capture more and more intricate patterns. But at this point we have to issue an important warning. This is where we risk running into overfitting. Overfitting is one of the most critical challenges in algorithmic trading, and we will address it in detail in upcoming lectures. Polynomials are not the only way to introduce nonlinearities that capture complex patterns. Another approach is to build features from Gaussian-like functions, each centered at different locations along the values of the chosen feature. Instead of rising one feature to higher and higher power, we create smooth, bell-shaped functions that activate in different regions. This gives our linear model the flexibility to push the position up or down depending on the value of the feature, and just like before, it can be done analytically and efficiently, guaranteeing the optimal result. In fact, in addition to powers of features or Gaussian-like functions, you can use anything else. Now let us look at the dependency of the optimal position on our feature range 15 when we use Gaussian functions. Interestingly, the result again suggests a trend-following strategy with a possible trend reversal around the minimum. But keep in mind, these results are for demonstration purpose only. They should not be taken as investment advice. In fact, what we are likely seeing here is another case of overfitting. So far we have seen how to build a linear model over many features, and we have also explored how to construct a non-linear model over a single feature. Within the very same framework, nothing prevents us from building a complex nonlinear model over many features. For example, suppose we have three features, let's call them x, y, and z. We can introduce nonlinear terms for each feature separately, just as we did before, by taking higher powers. But we can also go further and create interaction terms by multiplying different powers of different features together. Each of these new terms become a feature, and then, as always, we find the optimal coefficients using our analytical solution for the linear model that maximizes the Sharpe ratio. And with this we conclude today's lecture. If you learned something, please hit the like button. If you have any questions, suggestions, or requests, feel free to leave them in the comments. I will do my best to read and respond to each one. And don't forget to subscribe so you don't miss any new videos. Thank you.